No, there is no exception in the National Electrical Code to multiplying the connected load plus 25% of the largest motor by 1.25 if the connected load is over 800 amps. The formula for calculating the connected load of a motor control center, or MCC, is connected load equals the sum of motor loads plus 25% of the largest motor load times 1.25. This formula applies to all MCC, regardless of their amperage. If the motors in the MCC are not all running simultaneously, you can use a demand factor to reduce the connected load calculation. A demand factor is a percentage that represents the portion of the total connected load that is actually expected to be demanded at any one time. For example, if you have a MCC with 10 motors, each with a load of 100 amps, and you expect that only 6 of the motors will be running simultaneously, you could use a demand factor of 0.6. This would reduce the connected load calculation to connected load equals 6 times 100 amps plus 25% of 100 amps times 1.25 times 0.6, which equals 675 amps. Demand factors can be found in Table 430.25 of the National Electrical Code. The formula for calculating the connected load of an MCC is connected load equals the sum of motor loads plus 25% of the largest motor load times 1.25. This formula applies to all MCC, regardless of their amperage. If the motors in the MCC are not all running simultaneously, you can use a demand factor to reduce the connected load calculation. Let's delve into the specifics of calculating motor control center loads, focusing on the National Electrical Code requirements and the practical application of demand factors. The primary formula for calculating the connected load of an MCC, which we've already established, is connected load equals the sum of motor loads plus 25% of the largest motor load times 1.25. This equation ensures that the MCC is sized adequately to handle the continuous operation of all connected motors, with an additional safety factor for the largest motor. However, in real-world scenarios, it's often the case that not all motors operate simultaneously at their full rated load. This is where the concept of a demand factor becomes invaluable. The demand factor, as mentioned, is a percentage that reflects the proportion of the total connected load that is expected to be in use at any given time. It accounts for the diversity in motor operation, acknowledging that motors cycle on and off, operate at varying loads, or are used at different times of the day. To effectively utilize a demand factor, you must first accurately assess the operational characteristics of the motors within the MCC. This involves analyzing historical data, conducting load studies, or consulting with facility personnel to understand the typical usage patterns. For instance, in a manufacturing facility, some motors might be associated with equipment that operates continuously throughout the shift, while others might be linked to intermittent processes. The NEC provides guidance on demand factors in Table 430.25, but these are general guidelines and might not be suitable for every application. It's crucial to tailor the demand factor to the specific circumstances of your installation. Let's consider a more detailed example to illustrate the application of demand factors. Suppose you have an MCC supplying power to 15 motors, with the following characteristics. Firstly, 5 motors are rated at 20 horsepower each. Secondly, 5 motors are rated at 10 horsepower each. And thirdly, 5 motors are rated at 5 horsepower each. To begin, you would convert the horsepower ratings to amps using the appropriate NEC tables for motor full load currents. Let's assume that the 20 horsepower motors draw 25 amps each, the 10 horsepower motors draw 14 amps each, and the 5 horsepower motors draw 7.5 amps each. The total connected load would then be 5 times 25 amps, plus 5 times 14 amps, plus 5 times 7.5 amps, which equals 232.5 amps. Now, let's say that based on your analysis, you determine that only 70% of the total connected load is likely to be operating simultaneously. This means you would apply a demand factor of 0.7. To calculate the connected load with the demand factor, you would multiply the total connected load of 232.5 amps by 0.7, resulting in a demand load of 162.75 amps. You would then add 25% of the largest motor load, which in this case is 25 amps, to the demand load, giving you 162.75 amps, plus 6.25 amps, which equals 169 amps. Finally, you would multiply this sum by 1.25 to account for the continuous operation requirement, resulting in a final calculated load of 211.25 amps. This is significantly lower than the initial connected load calculation without the demand factor, which would have been 232.5 amps plus 25% of 25 amps times 1.25, equaling 304.69 amps. Using the demand factor allows you to size the MCC more efficiently, potentially reducing equipment costs and improving energy efficiency. It's important to note that the use of demand factors requires careful engineering judgment and a thorough understanding of the motor loads and their operating characteristics. Overestimating the demand factor can lead to undersized equipment, resulting in nuisance tripping, motor overheating, and potential equipment failure. Conversely, underestimating the demand factor can lead to oversized equipment, increasing costs and reducing energy efficiency. In addition to demand factors, there are other strategies you can employ to optimize MCC load calculations. Firstly, consider the starting currents of the motors. Motors draw significantly higher currents during startup than during normal operation. If multiple motors are started simultaneously, it can create a significant surge in current, potentially overloading the MCC. To mitigate this, you can stagger the starting times of the motors or use reduced voltage starters to limit the inrush current. Secondly, analyze the harmonic content of the motor loads. Nonlinear loads, such as variable frequency drives, can generate harmonic currents that can distort the voltage waveform and increase the overall load on the MCC. If harmonic currents are significant, you might need to install harmonic filters to reduce their impact. Thirdly, take into account the ambient temperature. The ampacity of conductors and circuit breakers is affected by temperature. If the MCC is located in a high-temperature environment, you might need to derate the conductors and circuit breakers to ensure that they can handle the load without overheating. Fourthly, consider future expansion. If you anticipate adding more motors to the MCC in the future, it's prudent to size the MCC with some extra capacity to accommodate the additional load. This can save you the expense of having to replace the MCC later on. Fifthly, ensure proper coordination between the overcurrent protective devices. The circuit breakers or fuses in the MCC should be coordinated to ensure that a fault in one motor circuit does not trip the main breaker, shutting down the entire MCC. This requires careful selection and setting of the overcurrent protective devices. Sixthly, verify compliance with all applicable codes and standards. In addition to the NEC, there might be other local or regional codes and standards that apply to MCC installations. It's crucial to be familiar with these requirements and ensure that the MCC complies with all of them. Seventhly, document all assumptions and calculations. It's important to keep a record of all the assumptions and calculations used in sizing the MCC. This documentation can be helpful for troubleshooting problems, making future modifications, and demonstrating compliance with codes and standards. Eighthly, consult with a qualified electrical engineer. Sizing an MCC can be a complex task, and it's always a good idea to consult with a qualified electrical engineer to ensure that it's done correctly. An electrical engineer can provide valuable expertise and guidance, helping you to avoid costly mistakes. Ninthly, perform regular maintenance and testing. Once the MCC is installed, it's important to perform regular maintenance and testing to ensure that it continues to operate safely and reliably. This includes inspecting the components for signs of wear or damage, testing the circuit breakers, and measuring the voltage and current levels. In conclusion, calculating motor control center loads accurately is essential for ensuring the safe and reliable operation of electrical systems. By understanding the NEC requirements, applying demand factors appropriately, and considering other relevant factors, you can optimize MCC sizing, reduce costs, and improve energy efficiency. Remember to always consult with a qualified electrical engineer and to follow all applicable codes and standards.